Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on furnaces and their operations in refinery or chemical plant. This will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to describe the various types of direct-fired heaters, explain the operation of an indirect-fired heater, apply the principles of heat transfer to fired heater operation, describe the basic components of a furnace, describe the different types of furnaces, describe common solutions to furnace problems. Before starting the course, let us have a look at key terms. A-frame furnace is a furnace that has an A-frame type exterior structure. Air preheater heats air before it enters a furnace at the burners. Air registers is located at the burner of a furnace. These devices adjust secondary airflow. Arch is a neck-like structure that narrows as it extends between the convection section and stack of a furnace. Box furnace is a square or rectangular furnace with both a radiant and convection section. Bridge wall is a sloping section inside a furnace that transitions between the radiant section and convection section, or the section of refractory that separates fireboxes and burners. Broken burner tiles are located directly around the burner and are designed to protect the burner from damage. The furnace rarely needs to be shut down to replace a broken tile unless it is affecting the flame pattern. Broken supports and guides tend to fall to the furnace floor. Missing supports or guides will result in tubes sagging or bowing. Burner alarms immediately notify technicians when a burner goes out. Cabin furnace is a cabin-shaped, above-ground furnace that transfers heat primarily through radiant and convective processes. Charge is the process flow in a furnace. Coking is formation of carbon deposits in the tubes of a furnace. Color chart of steel tubes shows 10 tube color variations associated with temperature. Convection section is the upper area of a furnace in which heat transfer is primarily through convection. Convection tubes are located above the shock bank of a furnace or away from the radiant section where heat transfer is through convection. The first pass of tubes directly above the radiant section is referred to as the shock bank. Cylindrical furnace is a cylindrical, vertical furnace, primarily designed to transfer radiant heat to a process stream. Draft is negative pressure of air and gas at different elevations in a furnace. Feed composition is the composition of the fuel entering a furnace, which must remain uniform, or furnace operation will be affected. Firebox is the area in a furnace that contains the burners and open flames, the area of radiant heat transfer. Flameout is extinguishing of a burner flame during furnace operation. Flame impingement is direct flame impingement occurs when the visible flame hits the tubes. Flame impingement can be classified as periodic or sustained. Flashback is intermittent ignition of gas vapors, which then burn back in the burner, can be caused by fuel composition change. Fuel pressure control loop includes a pressure sensor and transmitter, controller, transducer and control valve designed to maintain a constant fuel pressure to the furnace burners. Fuel pressure control is a pressure control loop located on the natural gas fuel line to the furnace that is designed to maintain constant pressure to the furnace burners. Furnace flow control is a critical feature in furnace operation, temperature, and pressure control that regulates fluid feed rates in and out of the process furnace. Furnace high/low alarms are warnings that warn when the process flow is off specification and prevent equipment damage and harm to the environment and human life. Furnace pressure control monitors furnace pressure in the bottom, middle, and top of the furnace with a pressure control loop connected to the stack damper. The middle pressure reading on the furnace is compared to a set point and adjustments are made at the damper if necessary. Furnace temperature control adjusts fuel flow to the burners, and, as flow exits the process furnace, monitors process conditions. The natural gas flow controller, slave, is cascaded to the master temperature controller. The temperature controller adjusts fuel flow to the burners. Hazy firebox or smoking stack often occur when not enough excess air is going into the firebox or the fuel-air mixing ratio is incorrect. Header box gaskets provide access to the terminal penetrations or bends on the convection tubes, also called header box doors. Header box doors and gaskets provides access to the terminal penetrations or bends on the convection tubes, also called header box doors. The gaskets provide a positive seal between the inside and outside of the furnace. Hot spot, a glowing red spot on the metal or refractory inside a furnace. Hot tubes glow different colors when the inside or outside of the tubes foul and when there is flame impingement, reduced flow rate, and overfiring of the furnace. Low burner turn down is a condition that can result in hazy firebox. Low NOx burners is a type of gas burner, invented by John Joyce, that significantly reduces the formation of oxides of nitrogen. Low NOx burners are 100% efficient as all heat energy released from the flame is converted to useful heat. Oxygen analyzer is an instrument specifically designed to detect the concentration of oxygen in an air sample. Oxygen flow rates are carefully controlled through a furnace. Peep blocks with peepholes are refractory blocks with holes in the center provide visual access that enable operators to inspect visually the inside of the furnace. Peepholes are holes in the side of a furnace that enable operators to inspect visually the inside of the furnace. Plugged burner tips cause flame pattern erratic, shoots out toward a tube instead of up the firebox. Preheated air is a compressed air system that typically pushes the air through tubes located in the upper section of the furnace. This preheated air takes full advantage of energy flow passing out of the furnace stack. Process heaters are combustion devices that transfer convective and radiant heat energy to chemicals or chemical mixtures. Process tubes pass through the convection and radiance sections as energy is transferred to them. This transferred energy allows the liquid to be utilized in a variety of chemical processes that require higher temperatures. Radiant tubes are located in a furnace firebox that receive heat primarily through radiant heat transfer, also called radiant coils. Refractory is the lining of a furnace firebox that reflects heat back into the furnace. Ruptured tubes causes flames come from opening in tubes. May cause excess oxygen levels to drop and bridge wall temperatures to increase. Sagging or bulged tubes occur when guides or supports break, when inside or outside of tube fouls, due to flame impingement, reduced flow rate, or overfiring furnace. Note, diameter of tube does not change when it sags, however, it does when it bulges. Shot bank are tubes located directly above the firebox of a furnace that receive radiant and convective heat. The shot bank is part of the convection section. Spalled refractory is an aging refractory that has cracked or deteriorated over time, a refractory that has not cured or dried properly, or a refractory whose anchors have failed, thus resulting in the refractory breaking loose from the sides of the furnace and falling to the furnace floor. Caused by old refractory that has cracked or deteriorated over time, or refractory that has not cured or dried properly, or broken refractory anchors. Stack is outlet on the top of a furnace through which hot combustion vapors escape from the furnace. Soot blowers remove soot from tubes in the convection section that consist of hollow metal rods that are inserted into the convection section and incorporate a series of timers that emit nitrogen in quick bursts. Terminal penetrations provide 180 degrees turns or pipe bends in the convection section as the pipes scroll from one side of the furnace to the other. Vibrating tubes tend to jump or move back and forth. Typically occurs in tubes outside the furnace. Vibrating tubes are often caused by two-phase slug-type flow inside the tubes. May be stopped by changing flow rates. Furnace applications and theory of operation. A furnace, that is, a fired heater, is a device used to heat up chemicals or chemical mixtures. Fired heaters transfer heat generated by the combustion of natural gas, ethane, propane, or fuel oil. Furnaces consist essentially of a battery of pipes or tubes that pass through a firebox. These tubes run along the inside walls and roof of a furnace. The heat released by the burners is transferred through the tubes and into the process fluid. The fluid remains in the furnace just long enough to reach operating conditions before exiting and being pumped to the processing unit. Furnaces are used in crude processing, cracking, olefins production, and many other processes. Furnaces heat up raw materials so that they can produce products such as gasoline, oil, kerosene, chemicals, plastic, and rubber. The chemical processing industry uses a variety of fired heater designs. These elaborate furnace systems can be complicated and equipped with the latest technology. Heat transfer. The primary means of heat transfer in a fired heater are radiant heat transfer and convection. However, heat must pass through the walls by conduction to be absorbed by the flowing fluid. In the fired furnace, the flame on the burner is the radiant heat source. Radiant heat transfer takes place primarily in the firebox. Tubes located in the firebox are referred to as radiant coils or tubes. The tubes transfer heat to the fluid by conduction. In a fired furnace, radiant heat is emitted from the combustion of natural gas or light oil. As the radiant heat travels from the bottom of the furnace, contacting the tubes or passing in the furnace, and then continues to the top, heat is transferred to the surrounding air. This process initiates the convective heat transfer process that causes the lighter air and hot combustion gases to rise above the radiant heat source. The top of the furnace is referred to as the convection section because most of the heat it receives is by convection. Combustion. Combustion is a rapid chemical reaction that occurs when proper amounts of fuel and oxygen, O2, come into contact with an ignition source and release heat and light. Furnaces use this principle to provide heat. Complete combustion occurs when reactants are ignited in the correct proportions. Incomplete combustion occurs in a fired furnace when not enough oxygen exists to completely convert all of the fuel to water and carbon dioxide. Many furnaces use natural gas or methane, CH4, as fuel for the burners. Methane, CH4, reacts with O2 to form carbon dioxide, CO2, and water, H2O. Incomplete combustion may result in the production of carbon monoxide. The chemical processing industry also uses ethane, propane, and light oils for fuel. Another common combustion reaction with oxygen is propane and oxygen form similar products to methane and oxygen. Fuel heat value. Different fuels release different amounts of heat energy as they are burned. The heat energy released, referred to as the heat value, is measured in British thermal units per cubic foot. The British thermal unit, BTU, is a measurement of heat energy. 1 BTU is the amount of heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. Hydrogen has the lowest fuel heat value, 274 BTU per cubic feet, whereas natural gas, or methane, has a heat value of 909 BTU per cubic feet. Charts are available that list the heating values of fuels used in furnaces. It is important to realize that the more tons of fuel gives off, the more oxygen is required for combustion. Basic components of a furnace. Fired heaters come in a variety of shapes and sizes. They have different tube arrangements and feed inlets and burn different types of fuels and have different burner designs. All furnaces do, however, have certain things in common: firebox, radiant tubes or coils, convection tubes, damper and stack, refractory lining, burners and air registers, fuel system, instruments, and induced or forced draft fans. Firebox and refractory layer. The section in a furnace that contains the burners and open flames is called the firebox. The firebox is lined with a refractory layer, a brick lining that reflects heat back into the furnace. The refractory brick is classified as fire brick or insulating brick, both of which are specially designed to withstand and reflect heat. Fire brick has a density range of 131 to 191 pounds per cubic feet and maximum temperature ranges between 2,500 degrees Fahrenheit or 1,371.1 degrees Celsius and 3,300 degrees Fahrenheit or 1815.55 degrees Celsius. Insulating fire brick has much lower densities, 27.3 to 78.7 pounds per cubic feet, and maximum temperature ranges between 1,600 degrees Fahrenheit or 871.1 degrees Celsius and 3,250 degrees Fahrenheit or 1787.77 degrees C. The refractory bricks are attached to stainless steel rods that are attached to 3 to 6 inch ceramic fiber insulation batt. The insulation batt and metal shell of the furnace touch. The insulation barrier between the furnace shell and brick prevents heat loss. The upper convection section and the arch section, the neck that narrows as it runs between the convection section and the stack, are usually insulated with heavy or light high-temperature cement, castable, or fire brick. Castable peep blocks contain peepholes that allow for visual inspection. Castables have a temperature range between 1,600 degrees Fahrenheit or 871.1 degrees Celsius and 3,300 degrees Fahrenheit or 1815.5 degrees Celsius. Typical heat loss from a furnace is between 2 and 3% of the total heat release. Since the insulation is porous, a protective coating may be applied to the inside of the steel shell to protect it from corrosive materials such as sulfur oxides. Temperatures inside the firebox range from 1,600 to 2,000 degrees Fahrenheit or 871 to 1,093 degrees Celsius. Furnace pressures usually run below atmospheric pressure in the range of 0.4 to 0.6 inches of H2O draft, negative pressure, at the bottom of the furnace. When the East Pass tube enters the firebox, it receives radiant heat directly from the burners. The West Pass tube enters the opposite side of the firebox and also receives heat from the burners. A bridge wall may separate the two passes in the furnace. As the charge, that is, process flow, leaves the furnace, the passes, tubes, enter a common header and are pumped to the processing unit. Radiant and convection tubes. The tubes located along the walls of the firebox are called the radiant tubes or coils. Radiant tubes receive direct heat from the burners. These tubes operate at high temperatures and are constructed of high alloy steels. Radiant tubes may be mounted parallel or perpendicular to the furnace wall. Radiant heat transfer accounts for 60 to 70% of the total heat energy picked up by the charge in the furnace. A color chart of steel tubes shows 10 tube color variations associated with temperature. Process technicians visually inspect these tubes and compare them to the color chart. Convection tubes are located in the roof of the furnace and are not in direct contact with burner flames. Hot gases transfer heat through the metal tubes and into the charge. Convection tubes usually are horizontal and are equipped with fins to increase efficiency. Convective heat transfer to the process charge accounts for about 30 to 40% of the total heat energy picked up in the furnace. This area is often referred to as the convection section. It is best described as the upper area of a furnace in which heat transfer is primarily through convection. Feed is introduced into the furnace through these tubes and exits out the radiant tubes. Tubes in this area are referred to as convection tubes and can be accessed through the header box doors at the terminal penetrations where the return bends or rolled headers are located. Rolled headers typically have removable plugs for maintenance and tube inspection. Air preheaters are often used to heat air before it enters a furnace at the burners. Air tubes are typically located in the stack or convection section that allow outside air to be brought in by a compressor or blower and gradually warmed up before mixing with fuel at the burner. Soot blower. Soot blowers are devices found in the convection section of process heaters. Soot blowing is required when the efficiency of the convection section decreases. This can be calculated by looking at the temperature change from the crossover piping and at the convection section discharge. Soot blowers utilize a transfer media such as nitrogen, water, air, or steam to remove deposits from the tubes. Air movement in the convection section is slower because of the thin tubes and close proximity of each pass. The initial blast of hot combustion gases tends to accumulate deposits here, specifically along the shock bank. There are several different types of soot blowers, wall blowers, and fin tube blowers. Furnace wall blowers have a very short lance with a nozzle at the tip. The lance has holes drilled into it at intervals so that when it is turned on, it rotates and cleans the deposits from the wall in a circular pattern. Soot blowing continues until a preset timer goes off. Stack damper. Combustion gases leave the furnace through the stack and are dispersed into the atmosphere at a height to ensure against any immediate deleterious effect such as carbon monoxide poisoning. As the hot air rises in the stack, it entrains combustion byproducts and carries them out of the stack. This natural draft creates a lower pressure inside the furnace that is essential to good operation. Draft is defined as the difference between atmospheric pressure and the lower pressure inside the fired heater. A damper in the stack permits adjustment of stack drafts. The stack damper is typically set to give pressures from 0.05 to 0.15 inches of H2O vacuum draft. At 0.05 H2O, approximately 350,000 pounds per hour of gas flow can be obtained. Some dampers resemble huge butterfly valves and require only 1/4 turn to be 100% open or closed. Other dampers resemble ordinary window blinds. Any rise in furnace pressure keeps secondary and primary air out of the furnace. The damper can be positioned to increase or decrease airflow. The different drafts or pressures found in a furnace. These readings are given by an inclined furnace tube gauge. Controlling excess oxygen in the furnace is the single most important variable affecting efficiency. For heat transfer in the firebox or radiant section, the greatest efficiency is obtained when maximum furnace temperatures are achieved. Decreasing excess air in the furnace maximizes radiant heat transfer. Excess airflow will decrease furnace temperatures around the burners and force the automatic controls to increase natural gas flow rates to the burner, wasting money. As hot combustion gases rise, cooler air is entrained, causing the temperature to decrease. Excess air enhances this process. When excess air is increased to the burner through the primary and secondary air registers, a temperature shift occurs as heat is moved away from the burners. Higher temperatures are found in the upper section of the firebox due to the reduced heat transfer in the lower section of the firebox. Temperatures in the convection section and stack will also rise significantly. This will reduce the amount of heat available for heating the hot oil, and more fuel will be burned in order to maintain process specifications. To be on the safe side, more air than is theoretically required for combustion is used. When this occurs, it is referred to as utilizing excess air. The percentage of excess oxygen by volume in the flue gas can be measured using a graph. Each fuel has its own plotted curve graph. Suppose, for example, that the oxygen analyzer digitally indicates an O2 reading of 3% by volume in the stack. The curve N as shown in picture shows this to be equal to 10% excess air for natural gas. Air can enter the furnace through open peepholes, leaks in furnace casing or joints, damaged header box doors and gaskets, burners that have gone out. It is important to recognize the position of the measurement, either near the burner or in the stack. Large leaks in the furnace can indicate high levels of oxygen in the system. Air-to-fuel ratio. Unit specifications require the console technician to decrease the excess air so that temperatures in the process heater will increase. As the excess air is decreased, the heat transfer rate near the burners is increased. Because the net heat released from the natural gas burner has not changed, the amount of heat contained in the hot combustion gases slows down and has time to soak into the exposed tubes. This process reduces the amount of heat transferred in the convection section and lowers the temperature in both the upper convection section and stack. This process provides a more efficient way to prevent heat energy from flowing out the stack. By decreasing the excess air flowing through the process heater, a technician can save money and more easily achieve product specification. Some process heaters utilize advanced control instrumentation that maintains a preset ratio of air to fuel. For example, a ratio of 11 means that for each weight unit, kilograms or pounds of fuel, there are 11 similar units of oxygen being supplied. Higher ratios indicate that there is more excess air. A lower ratio translates to less excess air. Theoretical air can be indicated in terms referred to as air-to-fuel ratio. When the air is specified in terms of air-to-fuel ratio, The amount of combustion air is calculated by adding 1 to the ratio and multiplying the results times the fuel rate. If the ratio is 11 and the fuel rate is 4 pounds per minute, this can be expressed as follows. Fuel rate equals 4 pounds per minute. Air rate equals 11 plus 1 is equal to 12. That is, 4 times 12 is equal to 48 pounds of flue gas produced by combustion. Burners and air registers. Burners can be arranged on the floor or the lower walls of the firebox. There are several types of burners. Oil burners set the proportion of fuel and air and mix them by atomizing the fuel with high-pressure steam or air. Pre-mix steam atomizing burners are internal mix atomizing burners that can handle almost any fuel and are widely used by industry because of this feature. They produce short, dense flames that are unaffected by wind gusts. Combination burners make furnace operation and fuel distribution more flexible because they combine two burners, gas and oil. This type of burner can use either gas or oil or both at the same time. Low nitrogen oxide (NOx) burners are designed to be operated with lower amounts of excess air than typical burners. The use of a tertiary air register reduces nitrogen oxides in the flue gas stream. Raw gas burners combine gas and air in the furnace, which ignite at the discharge. They use only secondary air, and the registers must be reset if the rate changes. Pre-mix burners pull in primary air for combustion through a Venturi-type air-fuel mixing device. They respond to changes in firing to keep the air-to-gas ratio relatively constant. Secondary air registers are provided in pre-mix burners. Burner alarms are located on each burner and will immediately alert a technician when a burner goes out or is functioning outside normal parameters. Air shutters on the burners control primary airflow into the furnace. Air registers near the burner control secondary airflow. These registers normally are closed when excess oxygen is detected in the furnace. The single burner in this system is a low nitrogen oxide system located on the floor of the furnace. Low NOx burners are designed to be operated with lower amounts of excess air than typical burners. The use of tertiary air registers reduces nitrogen oxides in the flue gas stream. The burner uses a small amount of steam to better disperse the fuel and oxygen. Air shutters on the burners control primary airflow into the furnace. Air registers near the burner control secondary airflow. These registers normally are closed when excess oxygen is detected in the furnace. A fuel pressure control loop is located on the natural gas fuel line to the furnace that is designed to maintain constant pressure to the furnace burners. The perfect mixing of air and fuel is impossible, and no practical way has been found to determine when the combustion process is complete. Incomplete combustion indicates that unburned vapors will be present in the hot combustion gases. To be on the safe side, most facilities use excess air to ensure all of the fuel has been burned. The burners are designed to avoid direct contact of the flames with the tubes in the firebox. A space of 1.5 to 2 feet is considered to be a safe distance between the open flames and the radiant tubes. The burner's flame pattern should be less than 60% the height of the firebox. The radiant section is engineered to distribute the radiant heat energy evenly. Modern burner design consumes 100% of the fuel with a nominal excess of 10 to 15% oxygen. Excess oxygen in the furnace is carefully controlled as it enters the secondary and primary registers. This control takes place as the fuel and primary air mix at the burner and is enhanced by adjustments on the secondary air registers mounted on the outside of the burner. An oxygen monitor carefully tracks the composition of the hot combustion gases. Adjustments to the airflow rate are made at the burners and the stack damper. The floor of the process heater has a 6 inches layer of heat-resistant castable, capped with high-temperature fire break. 4 ceramic high-temperature refractory blocks are positioned around the burner. The refractory system can withstand a wide range of high-temperature conditions. The refractory layer can be over a foot thick. The convection tubes in the upper section of the furnace have a variety of return bend designs. Bridge wall section. The bridge wall section is the sloping section of the upper furnace that connects the radiant section to the convection section. It is designed to accelerate the flow of hot combustion gases out of the firebox and into the convection section and stack. The bridge wall is the wall that separates the various sections in the firebox. The heat-reflective materials in this area are designed to withstand temperatures between 1,600 degrees Fahrenheit or 871.1 degrees Celsius and 3,300 degrees Fahrenheit or 1815.55 degrees Celsius. Forced draft process heater. Forced draft furnaces utilize a centrifugal blower to push preheated air to the burner for combustion. The preheated air is run through two coils located above the convection section and directed to the suction of a blower, that is, blower 100 shown in picture, which discharges under automatic control to the burner. Fuel system. Located under or on the side of the furnace is a complex network of lines that provides fuel gas and air to the burners. The fuel is stored in a tank located a safe distance from the furnace. In an oil burning system, atomizing steam and an oil preheating system are added to the network of pipes. Most injuries encountered in furnace operation occurred during startup of the fuel burning system. Feed composition is best described as the composition of the fuel entering a furnace, which must remain uniform, or furnace operation will be affected. The charge composition must also remain uniform, or variations in process variables will occur. Fuel pressure control utilizes a pressure control loop located on the natural gas fuel line to the furnace that is designed to maintain constant pressure to the furnace burners. Furnace flow control is a critical feature in furnace operation, temperature, and pressure control that regulates fluid feed rates in and out of the process furnace. Furnace high/low alarms are alarm warnings that warn when the process flow is off specification and prevent equipment damage and harm to the environment and human life. Furnace pressure control monitors furnace pressure in the bottom, middle, and top of the furnace with a pressure control loop connected to the stack damper. The middle pressure reading on the furnace is compared to a set point and adjustments are made at the damper if necessary. Furnace temperature control adjusts fuel flow to the burners, and, as flow exits the process furnace, monitors process conditions. The natural gas flow controller, slave, is cascaded to the master temperature controller. The temperature controller adjusts fuel flow to the burners. Furnace types. Furnaces can be classified by several features: type of draft, number of fireboxes, number of passes, volume occupied by combustion gases, and shape. Draft. Furnace draft can be natural, forced, induced, or balanced. In a natural draft furnace, buoyancy forces induce draft as the hot air rises through the stack and creates a negative pressure inside the firebox. This pressure is lower than normal atmospheric pressure. Forced draft furnaces use a fan to push fresh air to burners for combustion. Forced draft is used in furnaces that preheat the combustion air to reduce fuel requirements. In an induced draft furnace, as a fan located below the stack pulls air up through the firebox and out the stack. Balanced draft furnaces require two fans, one inducing flow out the stack and one providing positive pressure to the burners. Number of fireboxes. A furnace can have one or two fireboxes. A double firebox furnace has a center wall that divides two combustion chambers. Hot gases leaving the two chambers meet in a common convection section. Number of passes. The charge, that is, flow entering a furnace, is often split into two or more flows called passes. These passes usually are referred to as the east, west, north, or south pass. As the name suggests, each goes to a specific section of the furnace before they all enter a common discharge header. Furnace operators balance the flow rate of these passes equally before starting the furnace. Balanced fluid flow is critical during furnace operation. Another critical factor to be considered is the composition of the charge. The components that make up the charge must remain consistent throughout the duration of the run, or variations in operating conditions will occur. This could involve pressure, temperature, flow, and analytical variations to both the charge and furnace operation. Direct-fired and indirect-fired. Furnaces are classified as direct-fired or indirect-fired. The class is based on the volume occupied by combustion gases. In direct-fired furnaces, the combustion gases typically fill the interior. Direct-fired furnaces heat process streams such as heavy hydrocarbons, glycol, water, and molten salts. Cabin, cylindrical, box, and A-frame furnaces are direct-fired. Fire tube heaters are indirect-fired. They contain the combustion gases in tubes that occupy a small percentage of the overall volume of the heater. The heated tubes run through a shell that contains the heated medium. A fire tube heater resembles a multi-pass shell and tube heat exchanger. This type of heater is composed of a shell and a series of steel tubes designed to transfer heat through the combustion chamber, tube, and into the horizontal fire tubes. Exhaust fumes exit through a chamber similar to an exchanger head and pass safely out of the boiler. The water level in the boiler shell is maintained above the tubes to protect them from overheating. The term fire tube comes from the way the boiler is constructed. A fire tube heater consists of the boiler shell, fire tubes, combustion tube, burner, feed water inlet, steam outlet, combustion gas exhaust port, and tube sheet. Cabin furnace. The cabin furnace is a very popular direct-fired heater used in the chemical processing industry for large commercial operations. Most cabin furnaces are located above the ground, making it possible to drain the tubes and provide easy access to the burners, which can be located on the bottom, sides, or ends. Radiant tubes may be configured in a helical or serpentine layout. The radiant section in a cabin furnace is designed to contain the flames while avoiding direct contact with the tubes. A space of 1.5 to 2 feet is considered to be a safe distance between the open flames and the radiant tubes. The burner's flame pattern should be less than 60% the height of the firebox. The radiant section is engineered to distribute the radiant heat evenly. Modern burner design consumes 100% of the fuel with a nominal excess of 10 to 15% oxygen. Excess oxygen in the furnace is carefully controlled as it enters the base of the furnace. This control takes place as the fuel and primary air mix at the burner and is enhanced by adjustments on the secondary air registers mounted on the outside of the burner. An oxygen monitor carefully tracks the composition of the hot combustion gases. Adjustments to the airflow rate are made at the burners and the stack damper. The floor of the furnace has a 6 inches layer of heat-resistant castable, capped with high-temperature fire brick. Some cabin furnaces have a bridge wall that equally divides the firebox. A split-flow tubing arrangement exits the upper convection section as product flow drops down and into the hotter radiant section. These two separate pipe coils are also referred to as the North and South Pass or the East and West Pass. The refractory system can withstand a wide range of high-temperature conditions. The refractory layer can be over a foot thick. As hot combustion gases leave the firebox, a series of tubes, that is, the shock bank, is encountered. The shock bank in a cabin furnace receives the initial blast of the hot combustion gases. The tubes in the shock bank are the lower 2 or 3 pipe rows in the cooler convection section. The tubes in the convection section are designed to make use of the heat energy exiting the furnace. This process allows the feed to gradually increase in temperature as it moves through the system. Cabin furnaces have several advantages. They can accommodate radiant wall and in-firing burner designs. Their tubes can be drained, and their two-phase flows are less severe than a single-phase flow would be. Finally, they are highly efficient, ranging from 90 to 95%. Preheating the charge. During cabin furnace operation, the initial charge is pumped through a shell and tube heat exchanger to heat the fluid before it is sent to the furnace. Pumping this fluid through a preheater is efficient and saves money. Steam passes through the shell side of the exchanger as process fluid flows through the tube side. Flow control. flow is controlled upstream of the furnace. Feed may be split into 2 or more separate lines, the west pass, east pass, and so on. Each pass has its own flow control system. Cylindrical furnace. Another very popular direct-fired heater design used by industry is the cylindrical furnace. The simple cylindrical furnace is engineered to utilize the radiant heat that emits from the burner at the bottom center of the furnace. Heat transfer is primarily radiant unless special options have been added. The cylindrical nature of the furnace enhances draft from the lower radiant section through the optional convection section and out the stack. The vertical tubes are typically composed of alloy steel. The net thermal efficiency is around 60% for a standard cylindrical furnace, however, if a convection section is added, this rating jumps to 80%. A damper system to control airflow through the furnace is typically not used with a cylindrical design. Compared with other designs, cylindrical furnaces cost 10 to 15% less to construct, require less space and money to operate, have a higher firebox, have more parallel tube passes, and have higher flue gas velocity. A major disadvantage of cylindrical furnaces is that they have a lower efficiency than other designs because stack temperatures are higher. Box furnace. A box furnace takes its name from the square or rectangular design of the heating unit. This kind of furnace is best suited for oil firing. Burners can be on the sides or ends of the furnace. The firebox and radiant section use the roof, walls, and floor to reflect heat back into the firebox. Tubes may be arranged in a helical or serpentine layout. A bridge wall separates the radiant and convection sections. This wall may extend up from the floor or down from the ceiling. The refractory section in a box furnace is similar to that in a cabin furnace. Feed is introduced into a box furnace through the convection section and moves toward the firebox. Air tubes can be run through the convection section to warm up air that is being used for combustion. Box furnaces can use inlet and outlet fans to control draft. Induced, forced, natural, and balanced draft box furnace designs are used in industry. Common furnace problems and solutions. Large commercial furnaces are not frequently shut down unless a serious problem occurs or equipment repair and turnaround are scheduled. There are some common problems and concerns for which equipment must be continually monitored. Furnace efficiency. Running furnaces efficiently is a major operating concern because 2/3 of a plant's fuel budget is needed for furnace fuel cost. Furnace efficiency is linked to environmental regulations that stipulate a clean operation. Most furnaces use fuel gas or fuel oil. Natural gas burns cleaner and more efficiently than oil. In a natural gas furnace, oxygen and natural gas combine in the right proportions at the burner. In an oil-burning furnace, steam is used to atomize the oil and mix it with air at the burner tip. Primary air enters the furnace through air shutters located on the burner that premix air and gas within the burner. Secondary air enters through air registers located on the burner. Air also can enter the furnace through idle burners, open peepholes, leaks in the furnace casing or casing joints, or damaged header box gaskets. Ensuring proper air concentrations is critical to efficient furnace operation because the fuel burns cleaner and hotter. Incomplete combustion reduces heat output, produces waste gases, and creates a potentially hazardous condition as unburned fuel collects in the firebox. Safe, efficient furnace operation requires an operator to closely monitor and control the combustion process. Flame impingement. As flames reach up into the furnace, they occasionally touch a tube. Frequent or sustained contact is called flame impingement. This can weaken the metal tube and cause coking, which is the formation of carbon deposits in the tube. Flame impingement can sometimes be corrected by pinching back on the fuel supply to the affected burner. Hot spot. A hot spot can be identified inside a furnace as a glowing red spot on the metal or refractory. Sometimes hot spots can be corrected by redistributing the process flow so additional flow goes through and cools the affected tubes. Spalled refractory. Refractory that has broken loose from the sides of the furnace and fallen to the furnace floor is referred to as spalled refractory. This condition is caused by old refractory that has cracked or deteriorated over time, or refractory that has not cured or dried properly, or broken refractory anchors. Ruptured tubes. When flames are emitted from openings in the tube, this is an indication of ruptured tubes. These can cause excess oxygen levels to drop and bridge wall temperatures to increase. Vibrating tubes. Vibrating tubes tend to jump or move back and forth and typically take place in tubes outside of the furnace. Vibrating tubes are often caused by two-phase, slug-type flow inside the tubes. Such harmonic vibrations can be stopped by changing flow rates. Plugged burner. Plugged burner tips tend to make the flame pattern appear erratic as it shoots up and out toward a tube instead of up the firebox. Coke buildup. A certain amount of coking occurs naturally over a period of time inside the radiant tube section. Shutting down the furnace and injecting superheated steam can clean up this problem. Fuel composition. Changes fuels have different heat release rates that can be identified on standard charts. Fuel compositions change occasionally, and furnace efficiency also changes. Fuel composition changes can cause flashback, intermittent ignition of vapors that burn back in the burner. Operators must be prepared for these changes and make the correct adjustment. These adjustments include fuel flow rate, damper, charge flow, and burner alignment. Feed pump failure. If the furnace feed pump fails, the furnace immediately begins to overheat, causing coking and equipment damage. If the pump does not restart, put the spare pump online, isolate the primary feed pump, and have it repaired immediately. Flame out. Flame out occurs when the flame on a burner goes out with fuel still being pumped to the furnace. This situation puts unburned fuel into the furnace and creates a potentially dangerous situation. Flameout usually occurs when there is too much fuel being sent to the burner or when there is a loss of draft or oxygen. When this situation occurs, the furnace needs to be shut down. Broken burner tiles. Broken burner tiles are located directly around the burner and are designed to protect the burner from damage. The furnace rarely needs to be shut down to replace a broken tile unless it is affecting the flame pattern. Broken supports and guides. Broken supports and guides tend to fall to the furnace floor and result in sagging or bowing tubes. The falling supports and guides can also hit and damage a burner. Hazy firebox or smoking stack. Hazy fireboxes often occur when insufficient excess air is going into the firebox or the fuel-air mixing ratio is incorrect. Sagging or bulged tubes. As previously discussed, sagging tubes occur when guides or supports break. They also occur because of other factors such as when the inside or outside of a tube fouls and when there is flame impingement, reduced flow rate, or an overfiring furnace. Note that the diameter of a tube changes when it bulges. Hot tubes. Hot tubes glow different colors and occur when the inside or outside of the tubes foul, where there is flame impingement, reduced flow rate, or furnace overfiring. Valve failure. Furnace feed control valves are designed to fail in the open position. Valve failure cannot be detected until after an adjustment fails to respond. In any case, the operator will be unable to control the flow. Fortunately, bypass loops exist that allow the control valve to be isolated and repaired without shutting down the equipment. Furnace fuel gas valves are designed to fail closed. Furnace system. Running process heaters efficiently is a major operating concern because significant funds are expended on natural gas costs. Process heaters are also closely monitored by the Environmental Protection Agency for consistent clean operation and emissions. An advantage to using natural gas is its clean burning operation. F2O2 is a clean operating system that keeps excess airflow between 8 and 10%. Ensuring proper air-fuel concentrations is critical to efficient furnace operation because the fuel burns cleaner and hotter. Incomplete combustion reduces heat output, produces waste gases, and creates a potentially hazardous condition as unburned fuel collects in the firebox. Efficient, safe, process heater operation requires a technician to carefully observe and control the combustion process. Small commercial furnaces are not frequently shut down unless a serious problem occurs or equipment repair and turnaround are scheduled. There are some common problems and concerns for which equipment must be monitored. Simple startup procedure for furnace system. 1. Notify your supervisor and all concerned about startup. Downstream process technicians, I&E, engineering, maintenance, etc. 2. Ensure all safety hazards are secured. Trash, locks, old permits, etc. 3. Check equipment and instrumentation. Stroke control valves 0 to 100%, check lineups, etc. 4. Open PCV 100 to 100%. 5. Purge furnace for 15 minutes with steam. 6. Line up P100 to F2O2 and into TK100. 7. Set FIC 100 to 200 GPM. 8. Start P100. 9. Monitor process pressures. 10. Increase FIC 100 to 400 GPM. 11. Monitor process pressures and level in TK100. 12. Set AIC 100 to 3% and place in auto. 13. Set PIC 100 to 0.05 and CASC to AIC 100. 14. Set FIC 101 to 3,500 cubic feet per hour and place in manual. 15. Set AIC 101 to 21% and place in auto. 16. Light burner and allow F2O2 to come up to temperature. 17. Increase FIC 100 to 600 GPM. 18. Set FIC 101 to 8,500 cubic feet per hour. 19. Increase FIC 100 to 800 GPM and put controller in auto. 20. Set TIC 100 to 350 degrees Fahrenheit and put controller in auto. 21. Increase FIC 101 to 12,500 MVH and CASC to TIC 100. 22. Set LIC 1 to 75% and put in auto. 23. Cross-check process variables with spec sheet. Specification sheet and checklist. Furnace symbols. This picture shows the symbols for a furnace. Fired heaters or furnaces are classified as direct-fired or indirect-fired fire tube. In direct-fired furnaces, the combustion gases occupy most of the interior space of the furnace. In fire tube heaters, the combustion gases are contained in tubes, which occupy a small percentage of the overall volume of the heater. The heated tubes run through a shell that contains the heated medium. Cabin, cylindrical, box, and A-frame furnaces are direct-fired. Combustion is a rapid chemical reaction that occurs when proper amounts of fuel and oxygen come into contact with an ignition source and release heat and light. Furnaces use this principle to provide heat to the charge. Complete combustion occurs when reactants are ignited in correct proportions. Incomplete combustion occurs when not enough oxygen exists to convert all of the fuel to water and carbon dioxide. A combination of radiant, conductive, and convective heat transfer processes occur in a furnace. The methods of heat transfer that have the greatest impact in furnaces are radiant and convective. Direct-fired furnaces are used in many processes, including distillation, reactors, olefins, and other processes. Furnaces heat up raw materials so they can produce products such as gasoline, oil, kerosene, chemicals, plastic, and rubber. Direct-fired furnaces consist essentially of a battery of pipes or tubes that contain the process fluid and pass through a firebox. These tubes run along the inside walls and roof of a furnace. The heat released by the burners is transferred through the tubes and into the process fluid. The fluid remains in the furnace just long enough to reach operating conditions before exiting and being shipped to the downstream processing unit. Air enters the furnace through primary air shutters on the burners and secondary air registers on the burner. Air can also enter through the stack, peepholes, cracks in the furnace, and header box gaskets. Furnaces can be classified as natural, induced, forced, and balanced draft. Burners can typically be found in the following types: oil, pre-mixed steam atomizing, combination, low NOx, and raw gas. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.